Hello guys, and welcome in this new recording. As you know, lately I've been working on the introduction of the compute pipeline in my engine, so based on the WebGPU. And so I thought it would be a good idea to try to work a little bit more on a very simple example for how you can use those compute pipelines. And the idea I have for that is I'm going to try to build a minimal example where I have a compute pipeline that I use to update the content of simple texture. The idea I have is just to generate some kind of waves, moving waves from the center of the texture. And then after that, I would be using another a render pipeline this time to just display this texture with a simple quad in the scene. So what I want to do now is try to do that live, and so you would get a sense of how you can implement that. And maybe, yeah, you get a few ideas on how you could do that on your site. And let's just get straight into it then. Switching the view. So first thing I need to do is, as usual, I need to create a new example file. And for that, I'm probably going to start again with this simple scene, which is displaying the suburbs model currently, I think. Yes, with PBR processing. So I'm going to make a copy of that, prepare a duplicate example, and then resume the recording. All right. So here we are. We simply have three minor changes. In fact, I just created this new CPP file, which is a copy of the simple scene, as I said. And then after that, you also obviously need to specify that you want to create a new sample in your CMake system. So here we have it. So this is going to build an executable file called WGPU simple compute. And on top of that, I'm also preparing a small script. This is actually a Python script then, which is going to be executed with the nerve proj system. And this one is simply going to call this executable that we should have just created. After that, all I need to do is to build everything, including this new simple, which I already did in fact. And then you can just run the example with this command. And as expected, we get exactly the same thing as with a simple scene. Now let's just get rid of this PBR model in the center. So that would be, actually I can just do that live, I guess. I just want to keep control of the duration of this recording. So we need to remove this draw PBR. And actually from here, we need to figure out how to draw an additional model, which is going to be a simple quad, I guess. Not a screen aligned quad, but a simple quad anyway. And this quad would be using a texture. So first of all, I think I can already just create an additional texture. So to do that, we can just do auto X, and we're going to use the engine creator. That's going to be a texture 2D. And am I going to provide some data for that? That would be a good idea, I guess. So let's say we will have some image data, which is going to be a vector for my side. I need to create that first. The dimension of the texture, let's just say we're going to use a dimension of 256 for the width and the height of the texture, so a square texture. And then, as I said, we need to prepare the data that we're going to upload to this texture, and that, as I said, would be iData. Okay, and iData, you're going to We need to compute the number of bytes that we want to have, so that would be num bytes. That's going to be size times size, but for each pixel, we would have an RGBA format. So you need 4 bytes. So you need to multiply that by 4. And then you need to specify that as num bytes here when you create your vector to reserve the space that would be used for this. And it is accepted probably. And let's just make it completely white at first. And maybe just to not be really completely white, we should make one of the channels 0. How could I do that easily? I could get a pointer on the data. And then we're going to well, yeah, we can do that. We're just going to iterate on all the available pixels. So that would be 0 from like that. Whoops. And then what do we do? Let me cut this because it's going to take too long. All right, so it doesn't take that long after all. So what we have here is we start with an array which is full of the value 255, and then if you look at here precisely, we start from the beginning of this array, but we get an offset of 2, so it means you first start with the first pixel red channel, and then if you do +2, you will get to the blue channel. That's because the format we're going to use is this one, RGBA. So you get on the blue channel, and I want to set this blue channel to 0, and then I move to the next pixel, so +4 here, which means that technically the texture that we get at the end should have all the blue channel values set to 0. So we get full red, full green, that should be yellow, and that's it. So then you keep creating the texture, providing this data as input with the appropriate size. This format here is specified. One thing I should mention here already is, I believe you cannot use BGRA format if you want to write to this texture from a compute shader. I have been creating a unit test on this, and initially I was trying to use simply BGRA. Come on. Why? I'm not sure why, because usually I prefer using RGB, but this is the first thing I tried, and it would complain. The validation layer would complain that it's not compatible with the storage texture binding, I think. Probably you need to try that again if you want to be sure. Okay, so we have this format, and this is going to be used for texture binding, because we're just going to use that in a shader we want to display the texture. And in fact, when it's time to write to this texture, oh no, you would use storage binding in this case, I believe. So that would be, I mean, is this what we've been using? Let me just check the unit test. I'm going to come back to this unit test in another recording. That's the input, and the output, you need storage binding, yes. So let's provide that. Okay, so probably, well, we will start with just using the texture binding aspect, and then we'll get to the storage thing. Now that we have a texture like that, we need to render something to display this texture. And the thing that we want to render should be added to the scene. And it turns out that we have in the scene this draw function directly, which you can use to just provide a regular render node if there's no dedicated mechanism integrated in the scene class yet for that, which is the case here. So we're just going to create a WebGPU render node. And this node, well, it's not going to take any vertex input. I don't think that I need anything as input. I can just use the vertices, the vertex indices, I mean, and in the shader, and from that you could just build the position that you want to use. So we'll do that. And then you need to specify what is the shader that you are going to use. And I think there is already somewhere a simple texture shader or something like that. Okay, so this one is expecting the camera, a simpler texture 2D. All right. And for the input, oh, you are expecting some kind of input. So we can't really use that directly. We need to modify that if we are to generate the inputs inside the shader. So we're going to just make a copy of that, and that would be in the test. So test simple compute, all compute. No, it's not the compute part. So test or texture display, I don't know. Let's just say it this way. Okay, and now that we have this render node, we're going to add a simple draw call with, you actually need 6 vertices. Yeah, so something like that. And then you're going to provide your bindings. The bindings is going to be just a texture 2D on the texture that we created before. And that's it. And this is what you can add. So you can draw this here. Well, not quite. We need something else because the model here should react to the camera position. And maybe we should also throw transformation matrix in there. Let's keep it simple. For now, let's just provide the camera. Where is my camera? Good question. I mean, it's embedded in the scene or what? Or you can just use camera. I should do the trick, because it should be recorded with this name, I think, in the scene, right? Get or create scene. Let me check that and confirm it. Okay, so in my scene class, I am indeed creating a main camera for each scene, but this camera is not really registered in the engine itself, so using the name I mentioned just before here is not going to work. But the thing is, if you look at the scene itself, we can get access to the camera with get scene. So this is what we need to do here. We need to provide access to the camera. So this should also work. And then you can add this node. Then you also need to create this simple texture shader. So let me just prepare the skeleton for that and then resume the recording. Okay, so I just started from this file and I made a copy which I call simple texture here. And now let's go through this. First thing I see is we have a sampler here and a model that we are not providing. The model itself we can do without that for the moment, but the sampler is something that we will need. So let's just say, oops, sorry, it was noise. Let's just say we call that we just use bind linear sampler, and this should do the trick also. So we will have a sampler and the texture 2D here, and as output we provide the position, the texture coordinate, yeah, and the fragment position we don't need that. And as input, standard input, not quite. I mean, yeah, but you're not getting anything from there. And what do we have in the standard input? Do we have the index in there? I think yes. Sorry, I'm usually forgetting what I'm doing. So yes, we have the instance ID and vertex ID directly in the standard input, but we won't get anything else because all of this will not be defined. But we can use the vertex ID. This is all what we need. And what do we do when we prepare the output? I think we can first compute some UV coordinates. And to do that, it's again in the base utils. The function should be get quad. Yes, quad UV. So this function is going to start with your vertex ID. And the vertex ID in our case, as I said, we are going to render a simple draw call with 6 vertices. So the vertex IDs are going to be 0, 1, 2, 3, 4, 5. And this is exactly what you are expecting here. And depending on those values, then you just return what you could use as texture coordinates. A square texture coordinate from 0 to 1. And once you have those texture coordinates, you can just transform those coordinates and just produce simple position from them. So we're just going to do that. So you start from the UV and you call get quad UV from the input vertex ID. I think this is it. Now you want to turn that into a position. So the position, we could simply say you just build a vec4 from that. If we remember in WebGPU, the z-axis is forward, so you have x going right and y going up or down. I never know. Let's assume it's up. So what we want to do is to draw the quad on the x and y axis for now. So let's just use those coordinates, UV as x and y part, and then for the z, yeah, where is this going to go? I guess you can put 0. It's between 0 and 1 if you, well, we're going to transform that anyway, so let's just put 0 and 1. Okay, so that would be the virtual position, if you want, of the current vertex that you are drawing. Now you also want to consider that this position here is given in the world frame, so you still need to apply the camera transformation and projection. And to do that, we're going to use what is provided as UBO here. So the position that you get at the outside, it's actually what we have here written already. So remove that. And for the UV coordinates, you can just use what you just computed as UV here. And just currently, we don't have any model matrix yet. Yeah, I mean, not used. I just remove that. and you just transform the position using the view projection matrix. And the frag position, that's not really relevant, not needed for anything, so we can remove it. And after that, you will reach the fragment shader, and when you're in the fragment shader, you only have to do a simple sampling operation. You won't get this part. And that's it. I guess, in fact, since we're generating all the texture, we can just return the full color. This way we might be able to play a little bit with the alpha channel also. Alright, so what we have here should basically render a yellow quad. I guess this quad is going to be pretty small because the coordinates that we're using are really small. So we should probably grow this a little bit. So let's go back here when you compute your position, because UV here is going to be between 0 and 1. So what you want to do is to remove 0.5, and normally you would multiply that by 2 if you wanted to get clip coordinates, for instance, between -1 and 1. But in our case, as we said before, we're going to consider that this is the world position for the quad. So let's just say we want to go between -5 and +5. So we multiply that by 10. Okay, and okay, this was still running. Okay, so let's just rebuild all this. 22 minutes. Yeah, okay, let's see what we have. An error. Okay, give me a sec, I need to fix that. Okay, so the problem was when I get the camera here, it's a buffer provider, but we can't retransform that into a byte entry yet. So we need to call this as a UBO function. I mean, I think that's the only problem. Maybe not. Okay, we're good. So now let's see. Oh, cool. I mean, that's cool. And we can still, yes, move around. It's a simple quad. Is it displaying on the other side? Yes, it's displaying. Is it something I was expecting? I have no idea. Yeah, maybe somewhere when I create my render pipeline, I am disabling the culling, because you know you can, when you're rendering triangles, you can cull nothing, or you can cull the front face or the back face. And probably I have cull disabled, so it's going to render all the faces. Okay, so I have space to get back to the oh, come on. And now we need to handle the interesting part, which was to prepare a compute shader to transform this texture progressively. So once we have the texture, let's just also prepare this compute node. WGPU compute node, which we call C node. And for the C node, you're not providing any vertex format because there's no vertex provided as input. I mean, it's similar to what we have in this example here. So I guess probably I could just copy a part of that. That's a little bit of cheating, but yeah, let's say we have the right to do it. Let's copy that. And let's just prepare the shader here instead of linking that to a dedicated file. I could also have done that for this simple texture actually. So what we're going to do here is we want to write to an output texture storage, but we don't really have an input texture like this. So for now, let's just say this is the binding 0. Work group size 8 by 8. So I would also already mean a lot of threads in this work group. So we should not go higher than that. And then we have a global invocation ID, yes. And what are we going to do? We're just going to write something in the output. So let's just turn that into red for now. So let's have the value is going to be you need to write as float because the sampling that we have. I mean, how are you? Yeah. I guess it's what this means. You write as float, but then the storage itself is going to store byte values. So let's say you would like the output to be 1001 in RGBA format. And so this is what you're going to write here. And it means that if you run this even just once on your texture, then your texture should move from being yellow to red. So let's just pass this code to construct some compute shader here. And you need a compute step, right? So what do we do exactly? I don't remember. It's add. And then you have the dimensions for your step. So the texture is 2. We have the size specified anyway here, so we can use this size. Going to specify that here, and we need to divide that by 8. You probably need to ensure that you can divide that by 8, but in our case, it's the case. And so once you have those provided, you need to specify what are going to be your bindings. You actually need the actual bind group. Well, that's interesting. Maybe I should provide some additional support to be able to generate the bind group from bind entries. Let me check that. Oh, come on. Add. Yes, you're just expecting a vector of existing bind groups. There is some optimization that can be done here, which means that we need to create a bind group, which means that we need to define the bind group first. So we need to do that with the compute node itself. So that would be define group. Yes. The first thing that we have in this define group is simply the storage texture. To the yes, and you want to specify to write to the texture that we defined just before. Okay, and you can write to this, and that's all you have in your bind group layout. Then with that you can create an actual bind group, and again use the compute node to do that. Create bind group using the index 0 because that's the first bind group layout that we have defined. And again, you're just going to provide this because bind entries are used either to define a layout or actually build the corresponding layout, the corresponding bind group, sorry. So this should also work. And then you provide this bind group as a vector because you can have multiple of them. Okay. Normally, I would like to add this compute node as part of the scene. And in fact, it should be done before the render pass. So let me try to see how we can do that. All right. So in the end, this was a little bit more tricky than what I was expecting because there were a few things still missing in my own implementation here. So yeah, I have been modifying quite a few files because so we have this compute node, but we needed to introduce that into the scene itself. So we need a compute pass for that, and I had no support to provide a compute pass. So I have created this additional function here. With that, you can define a compute pass, which usually don't take any description. And the thing is, then when you have that, we start mixing compute passes and render passes in the scene. But those passes, there must be respecting the order in which you define them. To achieve that, what I did was to introduce some in the scene this simple structure here, which I call a generic pass, and in there you can have a pointer either to a render pass or to a compute pass, and then you just keep a vector of those generic passes. And now whenever I am creating a compute pass or render pass, I will populate the appropriate slot in this generic pass, and then when it's time to render everything, you get to this process function and you will encode the render pass that the pointer is not null in this case, and otherwise a compute pass. A bit tricky, but you need to handle this. What else? In the engine itself, I didn't have this encode compute pass, and I was yeah, there was a typo for the encode render pass itself. So this is a corresponding change in the scene. Quite a few stuff, because then whenever you have to draw PBR and so on, you have to handle this new concept of generic pass and so on. Here, this was a small issue due to the fact that here when I create bind group, I don't have any additional arguments, so the template function was a bit confused with that, and so on and so on. A few changes, and also I have introduced this compute method, which is similar to the draw method here, and you use that to introduce a compute node into an existing compute pass. And with this, what's happening now is in the scene, we have a first compute pass where you do some computation, and then you have a render pass where you do some drawing. Now let's just show you this. Bam! It's working as expected. Now we are actually, in theory, executing the compute pass on every cycle here, but since we just turned that to red, it just kept being red. And now next step would be to try to provide the time, a time entry for this computation to make this dynamic. And for that we can use what I think I called the frame provider, because the frame provider can provide you with the frame number, the current time, the elapsed time since the last frame, and this kind of information in a uniform buffer. So let's provide support for that. Okay guys, so adding the support for the time was slightly easier than the previous step. So what we're doing here is we're simply creating this frame context provider, and we provide this as an additional binding in the binding group. So we have this definition and the actual creation of the binding group itself. And now, in fact, since we have recorded that as a buffer provider, it's going to be updated on every frame when you're doing the rendering. So the frame number and the time that is specified in the corresponding buffer will be updated automatically. So you don't need to worry about that. And all we needed to add was the path in the shader where we are going to use this additional binding. So we have defined this frame UBO structure where you see that there is a time value here. This is now the first binding that we are providing in the group. And what we're going to do in the shader now is we're going to compute the distance of the current pixel with respect to the center of the texture. Here we're actually using fixed values, but I'm pretty sure we can get some dimensions from the context of the shader itself, and we have to investigate that, but not this time. Once we have this distance, I just added an arbitrary factor here, which is 0.5 to kind of grow a little bit the display, but this you could just not provide at all. It's just changing the visuals in the end. And after that, I initialize the value at 0 first, and then I'm going to check if the distance is smaller than 64 here. 64 is, if you consider that the center is 128, 60, and then you divide that by 2. So the maximum distance that you would get on a circle would be 64. If it's bigger than 64, it means you're not on the circle anymore, you're on the part of the square that are outside of the biggest circle that is contained in that square. And I didn't want to display those additional parts. And that's why I have this if condition here, and that's the only case where I'm going to put something in the value. Otherwise, we keep everything at 0. And since the value is then used for the red and alpha component, the color that you get here could be completely transparent if you're outside of the range. And finally, when you fix the issue and all, and you try to rebuild that, and you can finally start it, ta-da, it looks like that. Which is basically the idea I had in mind when I was starting this experiment. So we can still move around. We can see that at the border, yeah, the quality is not so good because at some point you're going to be fully red and there's no smooth transition. I could probably add some kind of smooth alpha transition on the border, but let's say that it's getting outside of the scope of this small experiment here. And basically, yes, this is it, folks. We can see that it's definitely not affecting the render rate or anything. And as small conclusion, so we have here now a mechanism where we can basically mix compute passes with render passes in the scene, and this is definitely opening the door to very interesting future construction. And this is it. So I hope you learned something, and I will continue to post those kind of experiments. So if you are interested in that, don't forget to subscribe. And that's basically all I have to mention on this one. Okay, so have a nice day and thanks for watching. See you another time. Bye bye.